Welcome, everybody. Welcome to the study back to the study of Newtonian mechanics. We learned about the laws before we went on our long weekend. Now we're going to move on our discussion to actually applying these laws. All right, now before we do that, let's have a short recap. So, what's a force? A force is a push or pull on an object. What does Newton 1 tell us about forces? Well, Newton 1 tells us that an object at rest will stay at rest unless a force that's an external force has acted on it. And then, what's this basically saying? Forces accelerate objects, right? And that brings us to Newton 2. Newton 2 tells us that the net force on an object is equal to the mass times the acceleration. I was seen it before in the book as A is equal to F over M, showing that the more force we have, the bigger force is, the bigger the force is, the larger the acceleration. The bigger the mass is, the slower the acceleration. So, nice. Then Newton 3 is basically action, reaction, pair forces. All right? If I have two particles, particle A and, oh my God, oops, particle B. Now imagine these vectors are equal, but the force that particle A puts on B, so force of A on B, should be equal to the force, the magnitude of force of B on A. You know, the force, so imagine that particle A, it puts a force on particle B, and particle B just returns that force in a different direction. So that's basically the third law in summary. There's so much clever algebra we can do with the third law to make math more efficient. So, yeah. Now, free body diagrams is a very important topic, but very simple still. But this is just a diagram where we list the forces acting on an object. All right. So now let's get started. So before break, we solved a common problem in Newtonian mechanics. All right, a block on an inclined plane. This is a classic problem. All right. So I want us to take us back to I'm gonna solve this one again here. So I'm gonna take us back a little bit just to remind us how to get through this kind of problem. All right. So if I have Earl the penguin, and Earl is sliding on an incline of 25 degrees with no friction. With no friction, what's its acceleration? And with friction, what's its acceleration then too? So step one, I need a coordinate system. But before I have a coordinate system, I need to know where the heck Earl is. Notice I'm just gonna draw a little box to represent Earl. All right? Or what? That's a diamond. I'm gonna have a little box just to represent Earl, or a circle, whatever. I don't need to draw a full penguin. All I need is the particle. All right. Oh, I want the box. Okay. Oh my God. Sorry, guys. All right. That'll do. Just imagine it's a symmetrical box. All right. Yes. So a little box. All right. That's Earl. I don't need to draw. I don't need to spend time drawing a penguin, and I can just draw a box to represent Earl. All right. So now, my coordinate system, because I'm on an axis, all right, because I'm on a slope, because I'm on a slope, basically, I can rotate my axis the same angle that it's away from the horizontal. So I can rotate in this case, I'm rotating my axis 25 degrees. And my positive y will be perpendicular to the surface, and my positive x will be the direction of motion arrow is going in. All right? So now, I have my coordinate system. Step 2 is a free body diagram. Free body diagram. All right? So let's draw the free body diagram of Earl. I'm going to draw it on the same triangle, just for convenience, basically, just so you can see the trigonometry that's going on here. All right. So, what force do I have acting on Earl? Well, Earl's on the surface, so of course, before you even say it's on the surface, the first force that I can think about is his weight force, is gravity. All right? And now, because he's on the surface also acts on him perpendicular to the surface as well. It's a normal force. All right? So, we are halfway there with the free body diagram. Now, because of how the trigonometry works, basically, we can calculate what the components of our weight force are. All right? We can see that here, if I kind of extend this down a little bit, just, in an imaginary manner, this here is a 90-degree angle, so it's a triangle. All right? And this over here, the angle that's over here, I call it beta, helps us analyze our component. So, if I have a 90-degree angle and my theta is equal to 25, I don't even need to find theta yet, but I know beta, I know for sure beta plus theta should equal 90 degrees. All right? For sure. That's true. That's because I already have a 90-degree angle, and all angles in a triangle equals to 180 degrees. All right? So, now, so if I extend my axis here, somewhere here. If I extend it a little bit, what do I think this angle is going to be? See, look, I have a perpendicular line, so I have another 90-degree angle here. And I have beta on one side. So because I know beta plus theta should equal 90 degrees, it's safe to say that to make this angle complete, that should be theta. Boom. So, and that's really, so because that's theta, we can now use this angle to calculate both omega y, this is omega y, and this line that connects here, that connects omega y to omega flat. Let me use a different color, hold on. This line here, forgive my drawing. These two are supposed to be the same size, but they're not the same size because of my artistic reasons. But this is going to be omega x. All right. So because it's omega x, this angle here, this line here is omega x as well. All right. So now we have a triangle. All right. We have a triangle now. All right. We have a little triangle there. We can break down our force into components. Before I do that, I'm going to just draw the free body diagram right here quickly. All right. Just so you can see what's going on. So I'm going to draw it in red. Yeah. So I have my Earl experiencing normal force. And then I have my Earl, because he, of course, is experiencing gravity as well. So we got my normal force, my gravitational force. So now we broke our vector into components, and we're experiencing a y component of weight, and the line that connects these two, that's the line I'm referring to there, is the same. Like, let me actually do it in purple as well. So if I change my color to purple, if I connect these two lines, you know, these are the same line, the vectors, and this right here is omega x, all right, and that's my theta. So that's my triangle. That's my free body diagram for my block on an inclined plane. At least for most questions, this is what it looked like. You have to be considerate about the scenario, but this is how the free body diagram works. You don't necessarily have to do all this beta, theta, angle stuff, but so long as you know that omega x and omega y, or wx and wy, if you like, are at least along the slope and perpendicular to the slope respectively. So yeah. Okay, so now let's find step 3. So what's step 3? What do you think step 3 is? Let's see. I would say a good one would be find magnitudes of omega x and y. All right, so okay, so we have our theta angle, right? So now this is something we've done several times already in class. So we're going to look for how to get cos theta and how to get sine theta from our triangle, and these will give us the magnitudes of the respective angles. So cos theta, if I have my relations here, my trig relations, let's see, so and ka, I don't need to put Torah. I'll put it just there for in case. So that's the opposite over the hypotenuse, right? Let's start with the sine. So what's the opposite angle here? The opposite angle here is omega x. All right. Now our hypotenuse here is omega. All right, this is our hypotenuse. And then now so if I cross multiply this, omega x is going to be equal to omega sine theta. All right, and then if I do the same thing here, I have my adjacent angle. My adjacent vector is omega y, sorry, not angle, and my hypotenuse is omega. Cross multiply, I can see that omega y is equal to omega times sine theta. All right. And we see that. So now, basically, the next step, actually, I'll put step 2 as the free body diagram and finding the magnitudes. All right. So then step 3. All right. Step 3. Find the forces in each direction. All right. Find the sum of. I have an iPad. I can just rewrite this. Okay. Step 3. Find the sum of forces in each direction. All right. Find the sum of forces in each direction. All right. So we have to say, so the sum of forces, all right, in the x direction, and we need to know the sum of forces in the y direction. So we're basically trying to find the net force in the x direction, net force in the y direction. All right. So what forces do we have in the y direction? We have the normal force, and we have the weight force. All right, the weight force. All right, and then this is how's the x direction. This is the y. I meant to put it for the y direction. I'm going to just slide that down. And then in the x direction, we only have omega. In the x direction, we only have the omega x. So if you see here, look at our axis. On the x direction, we only have omega x, and the y direction, we have the normal force plus the y component of the weight force. All right. So now here I just plugged in. I'm just giving the sum, but these have directions. So the y component of the weight force does not point in the same direction of the y component of the normal force. So this we don't have a plus there. We don't need to have a plus there. We need a minus sign. All right, because my positive y points upwards, and my negative y points downwards, and the y component, this guy here, points downwards, so it needs to be negative. All right. So anyway, because the normal force and the y component of the weight force are the same, they cancel each other out. So the sum of forces in the y direction is 0. All right, the sum of forces in the y direction is 0. Okay, so now, what about in the x direction? Well, in the x direction, we have the weight force pointing in the direction of motion. So we can just plug in for our weight force. Let's see, we have omega sine theta, weight x. All right. So what does Newton, because we've seen that we're not accelerating in the y direction, we could still be moving in the y direction, but we're not accelerating, we're moving at constant velocity. All right. So because we have a 0 in the y direction forces, that just means we're not accelerating in the y direction. So we can forget about that part. So now let's work in the x direction. And here we see that f of x is equal to omega sine theta, our weight. So now, basically, what does Newton 2 tell us? What's f of x? F of x is ma. All right. And then what's my omega? My weight. My omega is minus mg. All right, sine theta. All right. I want to find my acceleration. I want to find the acceleration of Earl. So I divide both sides by m. And I get A is equal to minus g sine theta. And that's the acceleration of Earl. If you want to find the exact number, just plug in g is equal to 9.8 and theta is equal to 25. Put it in the calculator and you get your answer. But that's just math, you know. This is the physics. The physics is here. All right? We've done the physics. All the physics is done. So that's how you find. So that's how you think about going about forces on an inclined plane. But now let's think about friction. Yeah, let's think about friction. Hold on. Without friction, our acceleration, I'm just really gonna put a is equal to minus g sine theta. But now with friction, let's see. I forgot to tell you what the friction coefficient is. Friction of 45 newtons. Yeah. So let's see. I'm just put a line there and say with friction, nothing much really changes except our free body diagram, and the force is not x direction. So if I just copy this guy, and then, oh my god, copy, and then paste, yeah. In the x, so my y direction stays the same, my x direction stays the same, but my weight is acting in the positive side of my y direction. So, where will my friction act? Friction always opposes motion, so my friction, oh my god, is gonna point to the negative side. Oops, come on, mate. Okay, that's good enough. The negative side, all right? So, now, okay, so that's, we've already done step 1, 2, and now we're moving on to step 3. All right, everything is still the same. We only have friction now. So the sum of forces in the y direction is still 0, all right? But the sum of forces in the x direction is the weight x. Now you see friction is pointing in the opposite side, in the negative side. If you go back to our coordinate, you know, our coordinate system this is our coordinate system. We have a positive y that way and a negative y that way. We see that friction is pointing to the opposite side, so it's going to be a minus f. All right, so at this point, after we solve our forces, we do the same thing. We apply Newton 2. And by applying Newton 2 just means we change f of x here, sum of forces to f of x. It's going to be ma, going to be equal to omega x minus f. All right, and we know what omega x is. We already solved for it, and we got it down. So ma is going to be mg sine theta, or minus mg sine theta rather, minus f over m. It's going to be a, it's going to be equal to minus g sine theta minus f over m. Whoa. So that's what our acceleration is. So F here is our friction. So I'm basically telling you that, like, let's think about what these things mean physically, yeah? So without friction, my acceleration is minus g sine theta. All right. So so it's just dependent on gravity and the angle I'm at. All right. Now, what about with friction? With friction, we have a factor here of minus f over m. All right. So basically, what I'm saying here is that if I have a really large mass, all right, a really large mass, I get more acceleration because this number actually, hold on, because a minus sign, a minus sign. Okay, let's be careful here. You know what? I think I'll just talk about this in class. But this is how to do it mathematically. All right? But this is the mathematics. Newton's law, when Isaac Newton posted his famous paper, a book rather, he named it the mathematical description of natural phenomena. All right? Physics is the study of natural phenomena through mathematics. So we need to be able to do these mathematics to describe the dynamics of the system. I hope this video helped give you a recap. All right. So now I'm going to move on to the second part of the new topics. All right. This is chapter 4. This is still chapter 4 stuff. Now we're going to look at chapter 5 stuff. All right. That's going to be in part 2. All right.